In this video, we'll be continuing our discussion about multiple linear regression. Now, regarding the assumptions on the error term, note that the assumptions are really all the same assumptions that we had before. So the error is a random variable with a mean of 0, which again using least squares is already done. That we have a constant variance, sometimes called homoscedasticity or HOV, but ultimately it means that the variance term is the same for all of the values. That the errors are independent, and this comes from the study design. Typically random sampling deals with this, and that the error is normally distributed around this particular construction of y. Really, it's just that the error term has a normal distribution. Now, there's a whole bunch of different tests that we can do for significance. We can do a test on every single one of the parameters, beta 0, beta 1, beta 2, beta 3, and then we also have this overall significance test. As we discussed before in simple linear regression, the f-test and the t-test for the slope were both the same, but now we have multiple t-tests, one for each of the slopes, and the f-test isn't going to be the same as any one of those. The f-test is going to be like combining all of those. Because of this, the f-test is the test of overall significance, and again, it shows if there's any independent variable or combination of independent variables that's significantly predicting the outcome. So the t-tests independently, one for each one of those parameter estimates, is going to be a test for significance on each of the individual variables. So for the overall f-test, again, our null is that all the values are 0, nothing's related to the outcome, and the alternative is that something's related to the outcome. The test statistic is the exact same as before because this MSR accounts for all of our new regression stuff. The only thing that changes is that the degrees of freedom changes. Now we have n minus the number of parameters minus 1 for the degrees of freedom. In this particular case, and excuse me, I shouldn't say number of parameters, n minus the number of independent variables minus 1 is how that notation works. So for our particular case where we have two independent variables, we're saying that both of the slopes are equal to 0. Note that this is not a test of the intercept, just of the slopes. And then we're saying for the alternative that one or more of these is not 0. We calculate our cutoff value, and then we can calculate our test statistic using software. So we've got the two mean squares of regression, the mean squares of the error, and we divide the two to get our f value. It is above the critical value, or of course we can just interpret the p-value. The p-value is lower than 0.05, so we determine a significant relationship. What does significant mean? Well, we have evidence to reject the null hypothesis. Reject null hypothesis. Null hypothesis, all the slopes are 0. Reject that. That means that something is not 0. So we have enough evidence to believe the alternative hypothesis that one or more of the parameters is not 0. That's what a statistically significant conclusion means here. So for each of the parameter estimates, you'll see this written as beta sub I. This isn't meant to confuse you. This is just because I could put a 1 in there, I could put a 2 in there. For more general, if I had more independent variables, I could put a 3 or 4 or 5 if I had 3 or 4 or 5 independent variables there. So it's I put a different number there depending on which one I'm trying to test. In this case, I'd have 3. I'd have beta 0, beta 1, and beta 2. So I just have my point estimate divided by the standard error, just like always for our test statistic, and I compare it to this t-distribution. The distribution has n minus p minus 1 degrees of freedom. And in this particular case, I'd be comparing to 2.11 as my critical value. I see that both of these test statistics are above 2.11, that critical value for my slopes. Both of the p-values are less than 0.05, so I can see that both of these are statistically significant. That is, that the experience that you have is statistically significantly related to your salary, and the test score that you have is statistically significantly related to your salary. Now, when I have multiple independent variables, I worry about this term called multicollinearity. Multicollinearity is just something that says that if my independent variables are too related to one another, they're not expressing a different thing from one another. I mentioned a time when our independent variables are too overlapping, we have a concern that maybe the fact that they're taking into account one another could be a bad thing, and I mentioned that I just did a presentation on this. Well, this is one of those cases. When I have multicollinearity, the fact that two things are explaining the outcome is not necessarily a good thing. So when I have very high correlation between the independent variables, there's not really enough extra from that to determine a real effect on the outcome after accounting for the other variables. There's a couple of different things that you can do here. Really, you want to avoid including these kinds of independent variables. So what you can do is you could combine both of these into a single variable. You could remove one of the problem ones. There's a couple of different things you can do. You could take the average of them and kind of combine them in that way. You could use, there's a fancy statistical analysis called principal components analysis that you can use to combine these. There's a couple of different ways that you can address this. But you want to be careful that your independent variables are expressing unique things about the outcome. So yeah, when your variables are highly correlated, you need to consider that. You can look at the correlation between variables to determine this. There's also a statistic that you can calculate called the VIF that you can use to calculate this. You don't want this to be greater than 10. This would be a bad thing if it were greater than 10. And R can calculate the correlation, obviously. I think we may have talked about this before. And it can also calculate the variance inflation factor, VIF. All right, so just like we could use the regression for estimation and prediction in simple linear regression, we can do that with multiple linear regression too. We simply sub in the different values of all the x values. Note that we need all of the x values to predict the outcome for y. Now in software, once I plug in all the x values, I have the predicted outcome of y, but in software I can usually just as easily as writing an argument like confidence interval equals true or something like that, ask for a confidence interval or prediction interval when I'm asking for the point estimate of the prediction. So if I have, let's say in our previous example, I wanted to predict the salary for somebody with a certain amount, let's say 5 years of experience and who scored an 80 on the aptitude test, I could come up with a predicted salary for that person and come up with a prediction or a confidence interval for that. All right, so for the residuals, we're going to talk about very similar things that we talked about before. Now, for the residual analysis, previously we talked about how I don't like plotting against x on the x-axis in the residual plot. I prefer to plot against a y hat. This is why, is because when we deal with multiple regression, y hat is what we need to plot against instead of an individual x value. So in this particular case, I am going to plot against y hat when I'm conducting my residual analysis, and then we'll also talk in the R session about a QQ plot that I use to assess normality instead of what the textbook shows. So again, we can look at these standardized residuals to assess if there's outliers in our model. This is important if I'm doing like more advanced statistical modeling. Here, I apologize, I said that wrong. This is important here. It becomes very important when we're doing more advanced statistical modeling and we don't necessarily have assumptions of things like normality. What we really look at is these standardized residuals, and we want them to be within about plus or minus 2. So for the residual output, I calculate my predicted y's, each of the residuals, that is how far off was the line from each of the observed points, and then I can calculate the standardized residuals using the format that we discussed before. Now looking at a list of residuals, I can kind of see how many break that plus or minus 2 barrier and by how far. So this observation number 2 breaks that barrier. So maybe that's one to keep an eye on. Looking at a graphic of the data points, again, recall when I'm looking at the residual plots, I really want to see no pattern among the plots. You may say that there's a little bit higher variability on the left side than the right side, and maybe we have a bit of a homogeneity of variance issue where it's narrowing down except for this outlier point up here. Again, it can be a lot worse. If I had another 100 data points that were looking like they were holding this pattern, I might be concerned. Typically, this is probably looking fine, though. Again, it has to really scream and jump out that it's a problem here, especially with that outlier, which would kind of bring this line to be a little more parallel. I'm not sure that it's of a huge concern, at least to me. Maybe I could kind of see it going both ways. If you were arguing this on a test and you said, yeah, it looks like it's narrowing in, I'd shrug my shoulders and say, sure. And actually, this is part of the art of regression is at what point does it become a violation or not? And there's not necessarily a good answer. It's interesting because this is where you'd think a statistical test can be helpful. And a statistical test could be helpful for making that objective distinction. On the other hand, very quickly we get to points where statistical tests are honestly provide worse recommendations than just looking at a plot and making a guess. So there's no real right answers when you get to this. It's part of the fun of, for me anyway, of this level of statistics as it becomes a little bit more art than science, and a good combination between the two. So it lets you use some professional judgment here. In my professional judgment, this could be considered borderline, but is probably fine. Now, I do notice that there is this outlying point up here. Now, do I consider this an outlier? What do I do with this? I have a, a joke on my office door that has somebody saying out, comma, liar, L-I-A-R, and then erasing the data point that doesn't agree with their theory. So don't erase outliers. That's never a good idea. But in this particular case, you may look at this and say, oh, yeah, that could be an outlier. It is above 2 on the standardized residual plot, but it's not anything crazy. So this is something that I'd look at. I'd kind of shrug my shoulders and say, meh. I mean, I could see if somebody said it's an outlier. I could also see if somebody said it's not too bad. For me, this is probably not too bad. I may, if I had some free time, go and check out why is this data point out there. And if everything checks out, then I would leave it in and not worry too much about it. Where would I get worried? If we're at about 3, 4, I've seen some that are like 10, 15, 20. Those are really bad ones that we really need to make sure we account for. But for this guy, again, our cut's 2. This is just a little bit above the cut. It's not something I'd be particularly concerned about. Well, in this discussion, we've discussed some of the details of multiple regression in addition to looking at the standardized residual plots and revisiting the assumptions. In the next video, we'll be discussing categorical variables and how we drop those into multiple regression.